Welcome to Mrs. Arel's Classroom Introductory Physics. In this video, we will practice Introductory Physics MCAS Open Response Release questions for heat transfer. We will start with number 44 released from the 2015 MCAS exam. Pause and try on your own first. Let's take a look at the information given in this problem. First, we will look at any graphs or diagrams given. It looks like we have a temperature versus time graph for two substances, stainless steel and iron. Stainless steel is circles on the graph and iron is triangles. Reading through all the questions is really important before you start answering. You can underline keywords and sketch any pictures to help you. A student was investigating cooling times for two pots made of different materials. One pot was stainless steel and the other pot was iron. The pots were placed on a table in a 25 degrees Celsius room. The pots are roughly the same size and shape and contain the same amount of water. The things that stay the same in an experiment are controls. The pots and water were originally at 100 degrees Celsius, and the student recorded the temperature of the water in each pot over time. The graph below shows the results. I created a little sketch of the situation, which is useful to do during an exam so that you don't have to reread the problem. There are two pots, stainless steel and iron, and they're at 100 degrees Celsius each initially, and they're placed in a room that's 25 degrees Celsius, so there's going to be heat transferred from hot to cold. We're going to have to determine the amount of time it took for the water in the iron pot to cool from 100 degrees to 60 degrees Celsius. Based on the graph, we'll have to look at which pot, the iron pot or the stainless steel pot, was a better conductor of thermal energy and explain the answer. Then we'll identify two methods of heat transfer that occurred as the water in the pots cooled, and also describe how the transfer of heat occurred for each method. Finally, we describe when the pots no longer experienced a net loss of thermal energy. So, I look at the graph and I note that the pots start at 100 degrees Celsius here. Then the iron reaches 60 degrees here. And I look at where the 60 degrees intersects the iron curve. It's at 1 hour. So based on the graph, the water in the iron pot cooled from 100 degrees to 60 degrees after 1 hour. Notice that I bolded the words that appeared in the question itself to help to focus my answer better. In number 2, based on the graph, which pot, the iron pot or the stainless steel pot, was a better conductor of thermal energy? I circled explain to remind myself that I have to do that. So first, better thermal conductor means that it transfers heat faster. A poor conductor transfers heat slower. So if I compare how long it took the stainless steel and the iron to reach 60 degrees Celsius, I notice that the stainless steel took an hour and a half, whereas the iron took 1 hour only. So based on the graph, the iron pot was a better conductor of thermal energy, or heat, because the iron pot cooled from 100 degrees Celsius to 60 degrees Celsius in a shorter time. You could have left it at that, or you could be more specific and state that it took the iron 1 hour in parentheses here, then the stainless steel pot, which took an hour and a half. In the third part, we'll identify two methods of heat transfer that occurred as the water in the pots cooled, and then describe how the transfer of heat occurred for each method. We can refer to the sketch I made earlier. As the water in the pots cooled, The two methods of heat transfer were conduction and convection. Notice again I bolded the words in my answer that I repeat directly from the question. Now I describe each method. During conduction, the water molecules transfer heat energy to the metal pot and the air by collisions. So if you imagine the water inside this container, the molecules of the water are colliding with the pot walls and transferring heat energy, and they're also colliding with the air molecules, and because the water molecules are hotter, they're transferring energy to the air. During convection, the hot water heats the air above and the hotter air moves up as the cooler air comes down. So if you again imagine this top layer of water here, and it's hot, it's at 100 degrees Celsius, it's heating up the cooler air above it. The cooler air becomes less dense and floats upward because it's lighter than the more dense air, and the cold air from up top falls down. It gets heated by the water at 100 degrees Celsius and gets less dense and floats up again. This is convection, the mixing of air and the transfer of energy of heat from the water to the air. Describe when the pots no longer experienced a net loss of thermal energy. So first, the pots no longer lose thermal energy or transfer heat, which is the same thing, when they reach the same temperature as the room. This is called thermal equilibrium. However, if we look at the graph, at 2.5 hours when the graphs stop, the pots are not at the same temperature. One is at 50 degrees Celsius and the other is at 40 degrees Celsius. So they're not yet in thermal equilibrium. And the room is at 25 degrees Celsius. So based on the graph, the pots have not yet reached the same temperature when the student stopped collecting data. Thus, at 2.5 hours, the pots are still losing thermal energy. Next, let's take a look at number 44, released in the year 2014. Pause and try to do the problem on your own first. Let's read through all the questions, underline any keywords, and sketch any pictures. A person brings a cup of hot chocolate 70 degrees Celsius into a room, which is at 20 degrees Celsius, and places a metal spoon, 20 degrees Celsius also as the room, into the hot chocolate. Sketching a picture may look like this, where you have the hot chocolate, the temperature of it is 70 degrees Celsius, the spoon is at 20 degrees, and the air is at 20 degrees. We're going to have to describe what happens to the temperature of the hot chocolate, the spoon, and the air in the room after 10 minutes. 10 minutes is a fairly short period of time. We'll explain our answer. Then we'll identify and describe the primary method of heat transfer. It could be conduction, convection, or radiation between each of the following. So we'll look at hot chocolate in the spoon, and then hot chocolate and the air in the entire room. Finally, we'll answer at what point will the net transfer of heat energy stop. Let's take a look at the first question. What happens to the temperature of the hot chocolate, the spoon, and the air in the room after 10 minutes? After 10 minutes, the temperature of the hot chocolate will decrease. The temperature of the spoon will increase, and the temperature of the air in the room will not change very much. So that states the answer, what happens after a brief period of time. Now let's explain the answer. Because the hot chocolate has a higher temperature than the spoon, heat is transferred from the hot chocolate to the spoon. Heat is always transferred from hot to cold. The spoon heats up and the hot chocolate cools down. So the spoon, which is initially at 20, its temperature will rise and the hot chocolate temperature will fall. Some heat is transferred to the cooler air from the hot chocolate, but there is much more air than hot chocolate to affect the overall room temperature. In part 2, we identify and describe the primary method of heat energy transfer: conduction, convection, or radiation. First, we'll look at hot chocolate and a spoon. The hot chocolate transferred heat to the spoon by conduction. The hot chocolate is in contact with the spoon, and the faster molecules in the hot chocolate collide with the slower molecules in the spoon. The hot chocolate transfers heat to the air by convection. But how does it do that? Convection is actually a combination of conduction and mixing. So the top layer of the hot chocolate transfers heat to the air that touches the liquid surface by conduction. And then this hot layer of air transfers heat to the rest of the room by mixing or convection. Hot air rises because it's less dense than the cooler air above, and the cool air sinks because it's more dense. And this keeps on going, this process of rising and falling. So you create, at what point will the net transfer of heat energy stop? Thermal equilibrium is when all substances reach the same temperature. Heat transfer stops when all objects reach the same temperature, which is approximately going to be the temperature of the room. This point is called thermal equilibrium. Because the room is so large, the temperature of the air is not going to increase very much from a small cup of hot chocolate. However, the temperature of the hot chocolate is going to decrease down to approximately room temperature. Now we'll take a look at number 45, released in 2011. Pause and try it on your own first. Let's read through all the questions, underline keywords, and sketch any pictures. On a hot day, a student places a glass of cold lemonade on a table outdoors. After a few minutes, water droplets have formed on the outside of the glass. Picture of this might look something like this, where you have the cold lemonade glass and the hot air surrounding it, and water molecules condensing or forming water droplets on the outside of the glass. So you have to think in terms of phase changes. You had gas, water vapor in the air, turning to liquid water on the glass, and that's called condensation. Is the energy absorbed or released by the cold lemonade? Explain your answer. Compare average kinetic energy for the air molecules and the lemonade molecules when the student first places the lemonade outdoors. Explain your answer. Right away, I think average kinetic energy, that's the same thing as what we call temperature. Explain how and why the water droplets form on the outside of the glass. Let's take a look at the first part. Is energy absorbed or released by the cold lemonade? Explain your answer. Cold lemonade absorbs energy from the hot air because heat energy is transferred from hotter substance to colder substance. That's the direction of heat transfer. So cold lemonade absorbs the energy from the hot air. Heat transfer stops when the lemonade and the air reach the same temperature, thermal equilibrium. This part is not necessary to get the question correctly. However, it does add to your answer to show depth that you know when heat transfer will actually stop, when energy will not be absorbed by the hot air, by the cold lemonade from the hot air. Here's part 2. Compare average kinetic energy for the air molecules and the lemonade molecules when the student first places the lemonade outdoors. So first places means it hasn't been that long. The lemonade just went outside, and then we'll explain. When the lemonade is first placed outdoors, the average kinetic energy of the air molecules is greater than the average kinetic energy of the lemonade molecules. Remember, kinetic energy is energy of motion, molecules moving around quickly if something is hot, and molecules moving around slower when something is cooler. So the air is hotter than the lemonade. It'll have faster molecules in it. Molecules of a hot substance, air, move faster and have more kinetic energy than molecules of a colder substance, which is lemonade. Explain how and why the water droplets form on the outside of the glass. So the air outside of the glass has water in it, which is called water vapor, and that's a gas. When the hotter water vapor in the air touches the cooler glass, the water molecules in the air release energy and become liquid water droplets on the glass. This phase change is called condensation. So when something is hot and condenses, it releases energy. This question is number 44, released in the year 2016. Pause and try on your own first. Let's read through all the questions, underline keywords, and sketch any pictures. During cold periods, many orange growers repeatedly spray their trees with water to prevent the oranges from freezing. If the air is cold enough, the sprayed water freezes around the oranges, leaving the oranges themselves unfrozen. So if I had to sketch a picture, I would place the orange in the middle, and it looks like they spray the orange on a cold day with water, and that water freezes into an ice layer surrounding the orange. We'll need to identify a measurement tool that orange growers use to measure the average kinetic energy of the air. Describe what happens to the average molecular kinetic energy of the sprayed water as it cools, but before it freezes. That's important because freezing implies a phase change, and cooling is not. It means the temperature is changing. So freezing is going from a liquid to a solid. Describe what happens to the average molecular kinetic energy of the sprayed water as it freezes. And explain how the phase change of the sprayed water may protect the oranges from freezing. So that's a thought question that applies the concepts of phase changing. Identify a measurement tool that orange growers use to measure the average kinetic energy of the air. Average kinetic energy of the air is the same as the temperature of the air. Orange growers use a thermometer to measure the temperature. The bold words indicate in part 2, describe what happens to the average molecular kinetic energy of the sprayed water as it cools but before it freezes or changes its phase. The average kinetic energy of the water decreases as the water cools. So lowering the temperature is the same as decreasing the average kinetic energy. Cooling happens when heat is transferred from the water to the air. Water molecules move slower, have less kinetic energy on average, and the water temperature decreases. Part 3. Describe what happens to the average molecular kinetic energy of the sprayed water as it freezes. So freezing is a phase change when a liquid transforms into a solid. That's where you get this ice layer. The average kinetic energy temperature of the water, which is a liquid, stays the same as the water freezes, which is a solid, because temperature stays the same during a phase change. The energy that's being released by the water. So during a phase change, the temperature doesn't change, but after the water is frozen, it can continue cooling again. Explain how the phase change of the spray water may protect the oranges from freezing. So, by forming this layer of ice around the orange, how does that keep the orange itself from freezing? During freezing of the sprayed water, energy is released from the water to the air and to the oranges. So the process of freezing is releasing energy. So the water turning to ice actually releases energy, and it releases it both to the air and also to the orange, actually warming it up a little. This phase change may protect the oranges from freezing by adding energy to the oranges. So the key concepts from this presentation are heat transfers from the hotter to the colder substance. Temperature is the average kinetic energy of atoms and molecules measured by a thermometer. Temperature change, not during phase change. What happens is molecules in a colder substance gain kinetic energy and move faster if they're being heated up. Molecules in a hotter substance lose kinetic energy and slow down if that substance is cooling. If you have a phase change when the temperature doesn't change, the substances release energy when changing from gas to liquid or liquid to solid. Gas to liquid is condensation, and liquid to solid is freezing. And substances absorb energy when going from solid to liquid, or changing phase from solid to liquid, which is melting, and from liquid to gas, which is evaporating.